Chapter 3: Embeddings. We have turned words into ID numbers, but those numbers are just labels, they carry no meaning. Now we give each token a meaning the model can do math with. We turn it into a vector. Here is the problem with token IDs. Cat is 3797, dog is some other number. But those numbers are arbitrary. 3797 is not bigger than or closer to 3796 in any meaningful way. The ID is just a name in a list. It tells the model nothing about what a cat is or that a cat is like a dog. We need something richer. The fix is an embedding. Each token ID is mapped to a vector, a list of numbers. Instead of the single label 3797, cat becomes a whole row of values. In a real model, that row might hold 768 numbers. This lookup table, one row per token, is called the embedding matrix. And every one of these numbers is learned during training. Now here is why a vector is so powerful. A vector is a point in space. And the model arranges these points so that similar meanings sit close together. Cat, dog, and kitten land in one neighborhood. Car, truck, and bus form another far away. Distance now means something. Meaning has become geometry, and geometry is something math can work with. So what do the individual numbers mean? Each dimension is a feature the model invented for itself. Nobody labels them by hand. But after training, directions in this space often line up with real ideas. One direction might track how animal-like a word is, another whether it is singular or plural. The model discovers these axes on its own, purely from predicting the next word. And this leads to something almost magical. Because meanings are vectors, you can do arithmetic with them. Take the vector for king, subtract the vector for man, then add the vector for woman. Where do you land? Extremely close to the vector for queen. King minus man plus woman approximately equals queen. The direction from man to woman is the same direction as king to queen. That direction encodes gender. How do we measure whether two vectors are close? We use the angle between them through a quantity called cosine similarity. It is the dot product of the two vectors divided by their lengths. When two words point in nearly the same direction, the angle is small and the cosine is close to 1, very similar. Point in unrelated directions and it drops towards 0. Cat and dog high, cat and truck low. One more crucial point. These vectors are not designed by a person, they are parameters learned. At the very start, every embedding is random. The words are scattered with no structure at all. Then, as the model practices next word prediction, it nudges the vectors. Words used in similar contexts get pulled together. Slowly, the cloud organizes itself into the meaningful map we just saw. So, embeddings. Every token becomes a vector, a point in a space of meaning. Close points mean similar words, and directions can encode concepts like gender. All of it learned, not programmed. But there is still one thing missing. The model sees a bag of word vectors with no sense of order. Next, positional encoding.